Recent discovery in chemistry.
Electron highway for hydrogen and carbon dioxide storage. Date, July 20, 2022. Source, Goethe University Frankfurt. Microbiologists have shed light on the structure of an enzyme that produces formic acid from molecular hydrogen, H2, and carbon dioxide, CO2. The enzyme of the bacterium Thermoanorobacter kivui was discovered a few years previously by microbiologists, and the scientists have recently presented its potential for liquid hydrogen storage. The filamentous structure of the enzyme, now described at atomic level for the first time, acts like a nanoiron and is evidently responsible for the extremely efficient conversion rates of the two gases. The researchers from Goethe University Frankfurt, together with the group led by Dr. Jan Schaller, University of Marburg and Loewe Center for Synthetic Microbiology, have now produced a molecular close-up of the enzyme. Through cryo-electron microscopy analysis, Schaller's group has succeeded in determining the HDCR structure at atomic resolution. This made details of the long filaments visible, which the enzyme forms under experimental conditions in the laboratory. In vitro, the filament's backbone is composed of the two small HDCR subunits, which are arranged together to form a kind of nanoiron with thousands of electron-conducting iron atoms. This is the only enzymatically decorated nanoiron discovered so far. On this wire, the hydrogenase module and the formate dehydrogenase module sit like mushroom heads on a cable, explains Schaller. The bacterium Thermoanorobacter kivui thrives far away from oxygen, for example in the deep sea, and uses CO2 and hydrogen to produce cellular energy. The HDCR of Thermoanorobacter kivui consists of 4 protein modules, one that splits hydrogen, one that produces formic acid and 2 small modules that contain iron sulfur. It was already clear to us after our discovery that it had to be the 2 small subunits that transfer the electrons from one module to the other, says Muller. In 2016, the researchers observed that the enzyme forms long filaments. Muller, we could see how important this structure was from the fact that filament formation massively stimulates enzyme activity. The team is convinced that not all the enigmas surrounding the HDCR enzyme have yet been solved through the atomic resolution of the structure. Jan Schaller says, "We don't yet know how the wire stores the electrons, why filament formation stimulates enzymatic activity so intensively, or how the bundles are anchored in the membrane. We're working on these research questions. But the HDCR's future could be very exciting," believes Volker Muller. "Perhaps one day we'll be able to produce synthetic nanoions which we can use to capture CO2 from the atmosphere. We're also a step closer now to biological hydrogen storage." This structure reveals why the HDCR enzyme is orders of magnitude more efficient than all chemical catalysts and far better than all known enzymes at producing formic acid as a liquid organic hydrogen carrier from hydrogen and CO2, cf. Background information. Volker Muller, the hydrogen concentrations in the ecosystem of these bacteria are low, and, in addition, the CO2 and H2 concentrations can switch. Formation of filaments and bundling not only substantially increase the concentration of these enzymes in the cell. The thousands of electron-conducting iron atoms in this nanoiron can also store the electrons from hydrogen oxidation intermediately when even just one hydrogen bubble passes by the bacteria.